room scheduling problem, where now we have some activities with start times and finish times. So each activity has a start time and a finish time. But now we have multiple rooms. So we would like to schedule now all the activities using the smallest number of rooms. So in the activity selection problem, we had one room, and our objective was to schedule as many activities as possible in that one room. Now we have these activities, but we have multiple rooms, and our objective is to schedule all of them using the smallest number of rooms. Okay? So now this problem, this is the room scheduling problem. Another name for the problem is interval graph coloring. Why is it called interval graph coloring? Because it's a special case of the graph coloring problem. So let's take an example. Example A1 is 1 to 4, or let's just A2, A3, A4. This is the start, this is the finish. So A1 starts at 1 and finishes at 4. A2 starts at 4 and finishes at 8. A3 starts at 2 and finishes at 5. And A4 starts at 6 and finishes at 7. And we would like to schedule these activities using the minimum number of rooms. Now, why is it called interval graph coloring? Because this problem can be represented as a graph. So activities that conflict with each other, so we can represent each activity with a vertex in a graph. So we have 4 activities. And if 2 activities conflict with each other, we introduce an edge between them. So A1, does it conflict with A2? No. Does it conflict with A3? Yes, so we put an edge. So this is a conflict edge. Does A1 conflict with A4? No, it doesn't. Now we look at A2. Does A2 conflict with A3?
Yes.
Yes, it does. And does A2 conflict with A4? Yes. And finally, A3. Does A3 conflict with A4? No, it does not. So these edges represent the conflicts. So there is an important problem in graphs, which is the graph coloring problem, where you are where the objective is to color the graph, to choose a color for each vertex in the graph, such that any 2 vertices that have an edge connecting them have different colors. Okay, so for example, I can color this, for example, blue. Then A3 and A4 cannot be blue because there is an edge connecting them. But A1 can be blue because it does not conflict with A2. So I can say this is blue. Then A4 has to have a color besides blue, any color, so I can color it red. Now A3 can have any color besides blue, so I can color it red. So here I managed to color this using 2 colors, which means in fact that I can schedule these activities using 2 rooms, because each color corresponds to a room, right? So the idea here is that if 2 activities conflict, they cannot be in the same room, which corresponds to they cannot have the same color. So the graph coloring problem is an NP-complete problem. It's a hard problem. But this room scheduling problem is a special case of it that can be solved easily using a greedy algorithm, the greedy algorithm that we are going to study today. why is it a special case? It's a special case. The room scheduling problem is a special case of the general graph coloring problem because the conflicts are caused by interval overlapping. So the cause of the conflicts in the case of the interval graph coloring problem is interval overlapping. So there is a definite cause of these conflicts. For the general graph coloring problem, things may conflict with each other for other reasons or multiple reasons, or in general, it could be any reason besides interval overlapping. So interval overlapping is just a special case of the general graph coloring problem, and it's a very easy special case because we are about to solve it using greedy algorithms. Now, you may be tempted to try to solve this problem using activity selection applied repeatedly. So if we apply activity selection repeatedly, apply activity selection repeatedly, what does it mean? So take room 1 and try to fit as many activities as possible in room 1 using the algorithm that we have studied in the previous lecture. So when we take room 1 and try to fit as many activities as possible in room 1, what will we get? So we'll go by the minimum finish time. So this is the minimum finish time. So I put A1. Then what's the next minimum? What's the next finish time? It's going to be this, A3. Does it conflict? Yes, so I skip it. So then I skip it. Next 7, does it conflict? No, so I can put A4. Can I put any other activities in room 1? What's that?
A2 would be better.
Well, I'm trying to apply the activity selection algorithm repeatedly. So the activity selection problem is going to consider the activities in the order of finish time. So I'm trying to show, in fact, that doing activity selection repeatedly is not going to give an optimal solution.
What if you interchange those two? Take the first ending one, one that ends first goes to the first room, then you find the next closest ending and you put it to the second room, and then you go back and forth like that.
So how can you generalize this? So we are looking for a general algorithm.
Then you would take the next closest ending and just put it into the next one. So you can do 2 arrays and just fill them up like that.
This is what we are going to do. We're going to do activity selection repeatedly. So we're going to do room 1. We can fit A1 and A4. Room 2. In room 2, we are left with 2 activities. So which one should we consider first? No, A4. Yeah, well, yeah, sorry, A3. A3, the one that we did not take.
Yeah.
So A3, so we take A3, but then we realize that A3 conflicts with A2, so we can only take A3. So we'll end up using a 3rd room. So here what I'm trying to make, the point that I'm trying to make is that if you use the algorithm that we have studied for activity selection, if you do it repeatedly, it's not going to give you an optimal solution. You will end up with 3 rooms in this case. So it's not optimal. Now if you try to patch it, it's you'll have to come up with something general. So it's instead of trying to patch this algorithm, we will just consider a totally different algorithm. We'll just look at the problem from a different view. So try to think of a different algorithm for solving this problem besides doing activity selection repeatedly. So activity selection repeatedly is going to give us 3 rooms, which is not optimal because we know that we can do it with 2 rooms. So one way of doing this is to consider the activities in order of start time. So, okay. So I will just, let me see. So we are done with this. So what if I look at
Sort by start time.
the start times? So what's the activity that will start first is A1. So S1 is going to be the first event. Then the next event is going to be the start of A3. Then what's the next? So I have at time 4, two things will happen at time 4. A1 will finish and A2 will start. So now the question, which one should I consider first, the finishing of A1 or the start of A2? Finishing of A1. Why? Because I'm trying to reuse the rooms as much as possible. So, I started with 1 and 3. I will put each one of them in a room. So this is S1 is going to be in room 1. S2 is going to be in room 2. Now, before I use a new room, I will use the finishing of A1 now to free a room. Now room 1 will be free after A1 finishes. So finishing of A1 is going to free a room. Room 1 will become free. Now this room, I can use it for the next event, which is the start of A2. I can put it in room 1. Right? Why? Because at this point, room 1 is free. So basically, the idea is to look at the start and finish events in time order, and first try to find a room that you have used before. If there is a room that you have used before, reuse it. If there is no room that you have used before, use a new room. You have no choice but to use a new room. So let's trace this step by step. So I'm going to trace this in detail. So we will look at, well, first let's see the events. The events are going to be S1, S2, then finish of 1, then start of 2, then at time 5 we have the finishing of as this is S3. This is S3. And at time 5 I will have the finishing of 3. Then at time 6 I have the start of A4. And at time 7 I have the finish of A4. And at time 8 I have the finish of A2. So just consider the events, the start and finish events in time order, but with finish considered before start. And the point in considering finish before start is what? Is to reuse rooms. Because finishing may free a room that I can use, I can reuse. So let's now look at for each event, for S1, S3, F1, S2, F3, S4, F4, and F2. These are our events. Now for each event I will look into the free. So first I have none. Okay, and I will look at the free list. So the free list initially has R1, R2, R3, R4, and then the assignments. Now with S1, R1 is going to leave the free list, and I'm going to assign S1. I will put S1 in room R1. Okay. Then I have S3. For S3, I will just use R2. So now I have R2, R3, R4. For S3, I'm going to assign S1 to R1 and S3 to R2. And now I have only R3 and R4 free. Okay? So I'm keeping track of the free rooms. Now finishing of 1, what is it going to do? It's going to free room R1. So now I have R1, R3, R4. And now, the assignment is S1 is no longer assigned to R1 and S3 to R2. But we can keep this anyway. Now S2. So we need a room for activity number 2. Now which room does it make sense to use? So reuse R1. So try to reuse rooms as much as possible. So R1 is the one that has been used before. So we reuse R1. So now I have R3 and R4. And I have S1 in R1, S3 in R2, and S2 in R1. Now 3 finishes. So this is going to free which room? S3 finishes. So which? R2. R2. Yeah. So now I'm going to have R2, R3, R4. Okay, and the assignment doesn't change. S1, R1, S3, R2, S2, R1. Now I need a room for S4, for activity 4. So which room should I use? R2. Reuse R2. Exactly. So now I have R3 and R4, and then S1 in R1, S3 in R2, S2 in R1, and S4 in R2. Then I have a couple of finishing events. So F4 is going to finish, so it's going to free up for R2. And F2 is going to finish, so it will free up R1. Okay, and of course the assignments are going to be the same. So these are the assignments. So basically the idea is to reuse rooms. Okay, questions? Yeah.
Is it after you after you do F1, R1 is still in S1, but then it's also S2 is in R1?
Oh, so it depends on what you mean here. But so I'm saying that yes, S1 has been assigned to R1. At this point in time, it's not in R1. So are you keeping the assignments, or are you simulating the current assignment? So if you are simulating the current assignment, yes, this should go away. Right? And this is not, shouldn't be there. And here, finishing of R3, so S3 goes in R2, so this should not be there. So now you only have one room, and so forth. So if you are simulating the rooms that are currently occupied, at any point in time you will not have more than 2 rooms. So you'll have at most, R1 and R2 occupied. So yeah, so whether you view it as simulating the assignments or just keeping the assignments. So here we're just keeping the fact that S1 is in R1. But at this point in time, it's not. Yeah.
Why are there 4 rooms?
Why are there?
Yeah, you just decided that we would use 4 rooms?
Okay, so who can answer this question? Why do we have 4 rooms? Yeah.
Maybe all the 4 timings may be overlapping, so we'll need 4 rooms for 4 activities.
Yeah, so basically we are using the worst case number of rooms. So we know that we have 4 activities. In the worst case, all of them will be conflicting with each other, and we may end up needing or using 4 rooms. So we just use the maximum that we may need. But we will never need more than 4, right? Yeah. Okay, so that's a good question. So now let's try to write the code for this, the code that implements this. Now this code, you know, what's the key idea here? So I will have to create the events. I will have to create some events. And, you know, the key idea is reusing. So how do you think I can implement reusing the rooms that have been used? How do you think this can be implemented? So whenever you need a room, you reuse a room that has been used instead of using a new room. Yes, please. What's that?
Rooms?
Well, yeah, that's a good idea. So basically, if a room gets used, then you put it on top of a stack or on top of a list, but you always look at the top of the stack or the top of the list for reused rooms so that you can, for used rooms, I'm sorry, so that you can reuse them instead of using new rooms. Yeah. Okay. So now, so you will need a list of free rooms. You will need some data structures like an event data structure that has 2 fields. For each event is either a start or a finish for a certain activity. So each event is a data structure that consists of 2 fields. The first field is start or finish. The second field is which activity. And for each activity, I need to keep at least the room that this activity has been assigned to. Okay? All right. So, and for each room, in fact, well, maybe we'll get to this later when we need it. So let me write the code. So room scheduling. And what do I take? So I take just S and F and N. S and F and N. So this is an array of start times, array of finish times, and this is the number n. So S, array of start times, and F is an array of finish times, and n is the number of activities. So first, create an array named events of size 2n, right? Because for each activity there is a start and a finish. Then sort the activities in events by time in ascending order. So now we have an array of events. So it's going to be like this. So this is the array of events, you know, S1, S3, F1. So you sort the events by in order of time. Then we need to create a free list and put n rooms in it. Why n rooms? Because that's the maximum number of rooms that we may need. Then for I equals 0 to 2n minus 1. So we go through the events from 0 to n minus. So this is 0, 1, 2, 3, 4, 5, 6, 7. Now each event is either a start or a finish. So start, finish. So let's call this the type field in the event. So if events of I dot type equals finish, if it's a finish event, what do? We free the room. So we look at the room that corresponds to this event. So the room is going to be room equals events of I dot activity. So we look at the activity for this event. Then we look for the room for that activity. So events of I dot activity dot room. So the event is start or finish slash then activity. The activity will have a room assigned to it. So we'll take the room for that event and free it or add it to the top of the free list. So we can say free list dot add to top of room. So we add room to the top of the free list. Okay. Else, let's see. Let's leave a line in case we need something. Usually there is something missing. Else, so if it's a start event, so what do we need to do? Yeah.
We have to assign
in this, if there is like 2 or more activities that are getting and finish at the same particular time, then
2 activities that finish at the same time.
yeah,
So when you sort them, it's like sorting an array. Right? When you sort an array and there are equal elements in the array, so they will be ordered arbitrarily, right? If you are sorting an array and the array has 2 5s in it, so the 2 5s will be ordered arbitrarily. So one of them will appear before the other. So if you have 2 finishes at the same time, so you will do, each one will have an iteration in the loop that will handle that finish. Okay, now else if it's a start, so what do I need to do if it's a start event? Yeah, assign a room. Where do I get that room from?
from the free list.
The top of the free list. Exactly. So room, in this case, room equals free list dot remove top. Or you can think of it as a stack, a pop. You can think of the free list as a stack. Stack is probably the most appropriate data structure. So in this case, you are popping the top of the stack. Here you are pushing. So here you are pushing. Here you are popping. Free list dot remove top of remove top. That's going to be our room. Now what do we do with this room? We assign it to this event. So we say events of I dot activity dot room equals this room. So this room is we are assigning this room to this to this activity. Okay? Now, what is missing? So we need to determine the number of rooms. So in order to determine the number of rooms, how do we determine the number of rooms that we have used?
Number of rooms minus the length of the stack. I mean, the number of rooms in the stack.
No, but the stack will have n rooms. The stack will, at the end, the stack will have n rooms. Right. Well, maybe you can keep track of the size of the free list. Right. So the minimum size of the free list, the minimum size that the free list reaches, you subtract that from the total number of rooms. That gives you how many rooms you have used. Right. So if you have 5 rooms and the free list gets to size 2 at minimum, then you have used 3 rooms. So yes, you can you can track the size of the free list, but you can also mark the rooms as used or not used. So you can have a class room that has in it a Boolean used, and then for each room j set j dot used equals false. So initially nothing is used. Then whenever you use a room, you set its field to true. So when you use this room dot used equals true, and then at the end you will have to scan the rooms to traverse the list of rooms and find a room that count the rooms that have been used. Okay, so now traverse the free list. Of course, at the end, the free list will be what? Will have all the rooms in it, right? Traverse the free list and count the used rooms. Okay? Yes?
You can just use a set, right? And then keep adding to that set, and at the end of it, just get the length of the set.
Use a set for what? For the free list?
Yeah, for the rooms that we've used.
Well, you just make a use room set and just add to that set too and get the length.
Okay. So, yeah, this is another way of doing it. Yeah, so basically you save the used rooms in a separate data structure. So you have a separate data structure for the used rooms, and then you count the number of rooms in that. Yeah. So there are multiple ways of doing this, but none of these will change the asymptotic complexity of the algorithm. So let's look at the asymptotic complexity of the algorithm. Well, why is it n log n?
It's like
Yeah, so sorting here is n log n. So the sorting is theta of n log n. And we just ignore everything that is n. So this is n. This is n. This is n. This is n. We don't care about the n's because we have n log n. And then the loop. What's the running time of the loop? It's theta of n. Why is it theta of n?
Because the inside operations are constant.
Are constant, yeah. So including the this is a push, and this is a pop. So the push and pop, adding to the top of the stack or to the top of the list, and removing from the top of the list, this is something that can be implemented in constant time. So before you say that this is a theta of n algorithm, you have to make sure that everything inside the loop can be implemented in constant time. So you want to make sure that you are not missing any hidden operations or hidden theta of n or something that is non-constant. But here, this is definitely a constant. This is constant. And this is pushing, can be implemented in constant time. This is constant, constant, constant. And of course, this final scan, if needed, it's going to be theta of n too. Okay, so this is the interval graph coloring algorithm. Now, and it's an n log n algorithm. Yes?
Professor, I don't know whether this statement is correct. The number of rooms we are getting used is equal to number of conflicts in one way, like A2 to A3. Then
the number of what?
Number of rooms are getting used is equal to number of conflicts we have in that example.
The number of what?
Conflicts.
Completes?
Conflicts.
Conflicts?
Yes.
Oh, the number of conflicts.
I don't know whether this statement is correct or wrong.
Well, the number of rooms that we are using is going to be equal to the maximum number of conflicts that we get at any point in time. So in fact, this is going to be the next issue, which is the proof of correctness. How do we prove that this is optimal all the time? So in fact, this can be proved much more easily than the activity selection problem. This can be proved using a bounding argument. So the argument to prove this is that at any point in time, if the algorithm chooses to use an additional room, so if it chooses to use room n, or let's call it k, that's because rooms 1, 2, 3 through k minus 1 have been used. So in this algorithm, so let's write this down. Yeah, so the idea here is that this algorithm will use a new room only if all other rooms are used. So let me explain this. So if at some point the algorithm chooses to use room k, it will choose to use room k because rooms 1, 2, 3 through k minus 1 are all occupied. What does it mean? It means that at this point in time, I have activities in rooms 1, 2, 3 through k minus 1. So I have k minus 1 activities that are active at the same time, at this point in time. And I'm adding another activity k. So this means that at this point I have k activities that conflict with each other. Okay, so basically I will not add a kth room, I will not use a kth room unless there are k conflicts at that point. And if there are k conflicts at a given point, you can never do it with less than k rooms. Right? So if there are k rooms that conflict with each other, you can never do it with less than k rooms. So this proves that the number of rooms that we are using here is going to be always within this lower bound, within this bound of the maximum number of conflicts. Okay, so any questions on this before we write it down? Any questions about this? So in fact, this is a different technique for proving correctness of greedy algorithms. So it's not based on greedy choice and optimal substructure. It's based on a bounding argument, an argument that sets a bound on the number of rooms that are used. And if the bound is the maximum number of conflicts that you can have at any point in time, then this is a valid argument. So if if you have the times 1, 2, 3, 4, so this is the time point, and this is the number of conflicts. So this is let's call it C1, C2, C3, and this is time n or 2n, and this is C2n. C is the number of conflicts at each point, and the maximum number of conflicts that you get at any point, C max, is going to determine the number of rooms that you need. Okay, so in this case, if you scan this, here I have 0 conflicts, here I have 1 conflict, 2 conflicts, 1 conflict, 2, 1, 2, and here I have no, I think it drops to 1, then drops to 0. So this is the number of conflicts that you have, and the maximum number that you got is 2, which means that you will need at least 2 rooms. Okay, so yes.
Doesn't that solve the problem a lot differently? Or
what do you mean solve the problem differently?
well, you say you just solved it, knowing that the answer is 2 rooms, right?
Yeah. Oh, so if you look at the if we are only interested in determining the number of rooms that we need, yes, you can look at the conflicts at each point, and then the maximum conflict is the number of rooms that you need. But usually we are interested in the actual assignment. Usually we are interested in doing actual assignments of events to rooms or rooms to events, to activities. So let's write this down. So the number of rooms, needed is not going to be, or is, yeah, let's write it this way, not going to be any better or smaller than the maximum number of conflicts that we get at any point in time. So the algorithm will use room K at a given point in time only if rooms 1, 2, 3 through k minus 1 are occupied. But this implies that at this point we have k conflicts. At this point we have k conflicts, which means that we need at least k rooms. Okay, so whenever you use a room, you use it because you must use it. There is no other way. Okay, so any questions on this algorithm? Okay, so now we have we have covered 3 different problems. The knapsack problem, fractional knapsack, we could solve it using greedy algorithms. We covered the activity selection problem, and we covered this graph coloring problem. We have proved the correctness of the activity selection problem and the knapsack problem using by proving the greedy choice property first, that we can start with a greedy choice. Then we use the optimal substructure property to prove that we can keep repeating this greedy choice for the remaining subproblems that will keep getting smaller and smaller until we get to a subproblem that is empty, until no more activities are left. For the graph coloring problem, we are using a bound-based argument. So this argument is based on a bound, or in fact a lower bound. So k here is a lower bound on the number of rooms needed. So we have basically proven that the algorithm will never exceed the lower bound in the number of rooms needed. And because at every point in time it never exceeds the lower bound, it's a provably optimal algorithm. It will never use more than what is necessary. Okay. Now keep in mind that this interval graph coloring problem is a special case of the general graph coloring problem. The general graph coloring problem, as we will see later, is an NP-complete problem. So it's not a problem that you can solve using a greedy algorithm. It's a problem for which nobody knows a polynomial time algorithm. So for the general graph coloring problem, there is no known polynomial time algorithm. Okay? There are polynomial time algorithms for easy special cases like the interval graph coloring. And this is, this applies to many NP-complete problems. So the general problem does not have a polynomial time algorithm, but it may have some special cases that have polynomial time algorithms. Okay. Okay. So any questions? Okay. So are there any questions on the homework assignment? Okay. So some students have been asking about the machine to use. So we are requiring everyone to make sure that their code compiles and runs on Athena so that we standardize things. But the timing results that you report the timing results that you report in your you write in your report do not have to be generated on Athena. In fact, they should be generated on a dedicated machine, on your own machine. Timing results will be more accurate if you are running this on your own machine and you are disabling all other programs and services on the machine. So it should be, ideally, the process that is doing the sorting should be taking 100% of the CPU time. No other process should be on the machine. But this is ideal. We try to approximate that as much as possible. So your timing results should be generated on your own machine. We have dedicated machines, by the way. We have labs with dedicated machines that you can use if you want. So there we have, I can give you the numbers of the labs that have dedicated machines that you can use for running the timing tests. Okay.